All right, I'm going to continue to talk about things that are about the thermodynamics, the statistical mechanics of complexity. But first I want to talk about what's a seemingly different subject, but it'll connect. Firewalls. And part of the discussion will involve a conjecture. It's a conjecture which I'm fairly comfortable with. My student Douglas, due to the fact that he never ever learned to think imprecisely, is skeptical about. Perhaps Douglas will say something about why is he here? Hi. I still have to teach you to think imprecisely. I don't know how that's going to happen, but anyway. I'm not going to go through the whole firewall story. I'm going to say what a firewall is basically a very, very high energy shock wave close to the horizon. A shock wave of the type that Stanford and Schenker studied. And Ahmed can comment about whether this is or is not what amps call a firewall. But I can call it a firewall if I want. And I'm not even sure you get burned by it. But I'll tell you what it is, and you can come to your own conclusions about whether you get burned by it. Imagine, well, let's start with our usual picture. One could have left this picture up, but I'll redraw it. Somebody in the remote past, in this double-sided black hole here, perturbed the system, let's call it at time TW, perturbed it with a low energy perturbation, a thermal energy perturbation, and that perturbation traveled into the black hole, blue shifted, and the further back it is in the past, the higher energy it will be throughout most of its history until it arrives up at this point here. If you go to the ultimate limit of taking this time way, way back, perhaps into the exponential past, exponential in the entropy of the black hole, you'll make what I would think of as an ultimate shock wave, which is as strong as anything that you can imagine. Remember, the energy of the shock wave grows exponentially with the time. We're going back in time an exponential amount. We have a pretty energetic shock wave traveling up along this horizon. Now, what will it do to you if it hits you? The most obvious statement is it has a huge, huge energy, and so it will burn you up for sure. On the other hand, since we know so little about trans-Planckian physics, it's not really possible to say with confidence. There's no way to analyze it at present. I will assume that this thing is a nasty firewall that will harm you if you try to pass through it, and in fact that it's pretty much the same kind of thing that AMPS was talking about. They may or may not agree. Okay, here's my question. We've already talked about what happens on the left side here when you create such a perturbation in the remote past, and in particular we asked to study the complexity as a function of the left time here. And what we found out is that the creation of this perturbation, originally we were in the white hole region. That's a region of decreasing complexity, analogous to a region of decreasing entropy, which of course is in many respects impossible. But the main reason why it's impossible is because it's unstable. You take a thing whose entropy is decreasing, even if you could set it up, you just flick it with your finger and very quickly the entropy will turn around. Same is true of the complexity, and we did the calculation. We found out that after a short period, basically a scrambling time, the decreasing complexity will turn itself around and start increasing. Okay, that was analogous, as I said, to the second law that tells you can't have, without instabilities, decreasing entropy. Okay, but now I want to look at it from the point of view of the right side over here in order to diagnose what's happening on the right side due to this shock wave going in here. And so instead of fixing the time on this side and studying it as a function of time on the left side, I'll fix the time on the left side and study the complexity as a function of the right side time. How do we do that? Well, we simply use the master formula, the Shanker-Stanford master formula, and plug in 0 time or any time that we like on this side. It's just important to fix it and to study what's going on as a function of this side. And I'll write down the answer, and we'll spend 2 minutes just looking at it. The complexity, which of course in this context, what the complexity means is just the volume of the minimal surface, or the maximal surface. When I say complexity, I mean the general relativity maximal surface. Okay, what we find as a function of the right-hand side is that it's equal to, first of all, the entropy of the black hole, and then the logarithm of the hyperbolic cosh of tau right over 2. It's really tau right plus tau left over 2, but I've set tau left equal to 0. And then plus, let's put it down here, e to the absolute value of tau w. Tau w is negative up here. This quantity is positive, minus the scrambling time, and then also, let's see, minus tau right over 2. In the general formula, there's also a plus tau left over 2, but I've just dropped that, and this is the end of the story here. Okay, now, this term as a function of tau right, I'm up in the upper right-hand corner somewheres. I'm not down below in the white hole region. I'm up above in what used to be, in any case, the black hole region. This tau right is, this cosh here is increasing. We take the logarithm of cosh, we get something linear in tau right, and that's just the usual growth of complexity on the right-hand side. But this term here is decreasing with tau right. And so there's a competition between them. And until tau right gets very big, so that this term is really small, the largeness of this factor here will overwhelm this, and this will be the bigger term. This will be the bigger term relative to this. This is decreasing, and so we find the odd behavior that by somebody poking at the left-hand side, they have created a situation where the complexity on the right-hand side is decreasing instead of increasing. Where's the crossover? Where does it eventually it will start increasing again. And to find out where it increases again, we just look for the crossover between these two, and that's easy to find. It occurs at tau right equals tau w minus tau star. This is the crossover point, and I'll interpret this for you in a minute. Once you move past that time, the complexity starts increasing again. Okay? So apparently, by throwing in this shock wave, you've created a situation where for some substantial length of time, I'm assuming TW is very big, for some very remote past, for some substantial length of time, the complexity on the right-hand side is decreasing, but not forever. Okay? The crossover point is here. I'm assuming tau w is very big, much bigger than tau star, so that's a fairly long time. Let me draw a picture of, I'll draw it over here. I'm going to use a diagram which is not a Penrose diagram. I am very resistant to not using Penrose diagrams. I don't like using these diagrams of people who explaining it to their grandmothers, explaining black holes to their grandmothers use, but I'm going to do it anyway. What do I mean by a diagram that I used to show my grandmother how black holes work? I mean Eddington-Finkelstein coordinates. Okay? In Eddington-Finkelstein coordinates, you draw the singularity as a vertical line. Time goes up. Here's the horizon. Out here is beyond the horizon. This is the interior region. The only thing which is odd is that the signature of the metric in here is such that time is space-like, but ignore that. And I want to draw another region here. The other region I want to draw, I'll draw it in pink. This is a kind of stretched horizon, but an inner stretched horizon behind the horizon, and it corresponds to things which are a Planck length from the horizon. Let me expand that out a little bit so I can draw my picture. This line here is a Planck length from the horizon, say, roughly a Planck length. And by going, there's also one on the right-hand side here too. That would be what people normally call a stretched horizon. I'll just call this the inner stretched horizon. And what's true is if I send this shock wave in from the remote past, then the shock wave starts out very, very close to the horizon and spends a long time in this super-Planckian region. That's when the energy of it is enormously high. I will assume that anybody who tries to pass that doesn't survive, but that's all right. And then with time, as time goes on, as the shock wave climbs out of the deep black hole, it loses energy and it starts to move away. At the time when this crossover happens, let's put the crossover time right over here, tau W minus tau star. That's exactly when the shock wave crosses out of the Planckian region. It crosses out of the Planckian region at that point, and then in a fairly short amount of time, namely t star, it falls into the singularity. This is tau W over here. So here's the picture. During the time when the shock wave is a very, very intense super-Planckian shock wave, the complexity is decreasing. Okay? Once we get to the point where the shock wave crosses out of the super-Planckian region, that's where the complexity starts to increase. But at first it starts to increase slowly compared to the natural rate of growth. The natural rate of growth would be entropy times temperature. Okay? This shock wave doesn't disappear completely. It's behind here, and during this period, until the shock wave falls into the singularity, the complexity is growing, but growing slowly compared to what the expectations normally. It speeds up, but just about over here, when the shock wave falls into the singularity, the complexity growth resumes at its normal rate. Okay? What I would conclude from this is that high-intensity shock waves like this, super-Planckian shock waves, are associated with decreasing complexity. As a consequence of being associated with decreasing complexity, they're unstable. All you have to do, even in this period when they're very, very close to the horizon here, all you have to do is throw in one thermal photon, and that will push the shock wave in such a way that in a relatively short amount of time, it will depart from the Planckian region. That can be worked out. Okay, so firewalls are associated with decreasing complexity. How did we make decreasing complexity? It's like making decreasing entropy. Well, we did something extremely difficult by running backward in time and throwing in the shock wave from this point here. It's what we were talking about with Juan earlier, that to send in a shock wave like this, you have to do something quite complex, and that quite complex means running the system backward with the Hamiltonian, throwing in the shock wave, and coming back out. So you've done something unnatural, so to speak, And what you've gotten is something unnatural. Good. All right, so that's not the conjecture. This is mathematically proven to the highest quality mathematical proof. The conjecture is the following, that even without that shock wave, if we wait long enough, and I have to put in a caveat here, if we're not in the exact thermal field double state. Oh, in fact, we could even think about this in the context of one-sided black holes. I think the best context would be one-sided black holes. That if we wait long enough, if we follow the increasing complexity, and we wait an exponential time, a transition happens, and the transition happens to equilibrium where the complexity is no longer increasing. It's not thermal equilibrium. That was long ago. That was way down in the corner here. But complexity equilibrium, where the quantum complexity stops growing and something happens. In fact, I think I showed you in the first lecture that what you might expect is that the actual complexity is a jagged function which goes up, which goes down, which goes up by little bits. And so there will be periods in here when the complexity is decreasing, periods when the complexity is increasing. And the conjecture is that there is a significant probability at this time for discovering a firewall. If Bob jumps into the black hole at this very late time, the conjecture is that he's endangered by the fact that the complexity has stopped growing, and therefore the wormhole has stopped growing. New space has stopped being produced. And so that's the conjecture, and I think Douglas's argument, Douglas is not against this view. He just says there's no way to analyze it, and I agree with that. I mean, there's no known way to really analyze seriously what happens at these exponentially late times to somebody falling in. So I'll take it as a conjecture. It fits together with other things I know, but it might be wrong. Oh, let's suppose it's true, though. Yeah.
Wouldn't the fact that the wormhole stops growing be something bad that happens deep inside and not? The wormhole is growing in this vision.
I think the whole thing collapses and goes into something bad. I don't know. That might be the case. The AMPS people, particularly Joe Polchinski and Marolf, claimed with an argument that I never really understood, is that when you get to a generic state, a truly generic state, that firewalls will occur. Now, I've never completely understood that. I'm going to take it as a sort of gospel that our Santa Barbara friends knew what they were doing. But what they missed was what a truly generic state means. They thought a truly generic state meant a thermal equilibrium state, a state that was scrambled. A truly generic state is one which is exponentially complex. So I'm going to take it on faith for the time being that when you hit this very late time, as long as you don't have the exact symmetry of the thermal field double state, that there's a good probability that you'll hit a firewall. Now we can, and I'm simply not prepared to give a stronger argument. What's that?
Could I make a comment?
Yes, absolutely. Please do.
One question?
Yeah.
I think one argument that the wormhole stops growing at that time is based on the idea that the wormhole represents something like a minimal tensor network that prepares the state.
Mm-hmm.
And it's likely that the minimal tensor network will be a random-looking tensor network everywhere, not just inside the wormhole.
That's right. I can add one more thing to that, the discussions with, if you wait truly long enough, if you wait for quantum recurrences to happen, on the way down, when the complexity is decreasing, you will surely create firewalls. So allow an old man his prerogative of making a speculation which will not be, which I think is probably too hard to confirm now, But let's follow it. Okay, so here's an interesting fact. The time at which, or the complexity at which the transition happens is someplace with a complexity of order 2, I'll call it 2 to the k. I really mean entropy, but thinking in qubit language, 2 to the k, where k is the number of qubits. That's the place where it maxes out. Since the complexity along here is increasing linearly, then there's also a time of order 2 to the k where that happens. Supposing we now perturb the system by adding 1 extra qubit to it. That could mean just throwing in a thermal photon. Throwing in a thermal photon increases the entropy by 1 unit. And so what does it do? It takes the complexity from 2 to the k to 2 to the k plus 1. K plus 1 is not important. It's just a small change in k. But it really is twice 2 to the k. Now this formula over here, that 2 to the k plus 1 is twice 2 to the k, I had completely missed. It was worked out and proven by 2 people, by Tom Banks and Adam Brown, and I'm thankful for them for the proof of this formula. I completely did not realize it, but the point is, this doubles the maximal complexity. You have bought yourself an additional amount of complexity that you can increase by, which goes from here to here. So if I throw in that photon at some point, I now create a situation where the complexity is allowed to increase again for another exponential time. What's the conclusion? The conclusion is by throwing in a thermal photon, you can restore the system to, you can restore the youth of the system, so to speak. A fountain of youth, which is just one thermal photon's worth of energy thrown into the black hole, restores its ability to continue to grow for another exponential amount of time. Okay, now that's a lesson that I want to keep in mind as we go forward. That's all I'm going to say right now for the issue of firewalls. The point is they're fragile. They're fragile. Throwing in a photon of thermal wavelength will, after a scrambling time, destroy them. Or another way of saying it is it'll hit them and knock them into the singularity. Now I want to get back to the thermodynamics of complexity. And by thermodynamics now, I mean thermodynamics in the sense that 19th century steam engineers would have thought about it. How do you use, or how they would have thought not about complexity, but entropy, yeah.
So during the linear growth period, I would expect there is also some noise, right?
I think there's a lot less noise, but yeah, there's a lot less noise during that period.
So is it also dangerous that I might find also firewalls during the linear period?
Oh, I think there's a small probability, but I think it's extremely small. But come to me afterwards and I'll explain. I've already actually explained it in the first lecture, but you know, it's a long time ago. I showed you on those figures of trees how as you move out along the tree, the complexity grows with tremendous likelihood. It increases and increases linearly. And then when you get to maximal complexity, you flip around to some other place. That's where the noise starts. Right. That's where serious noise starts. And so, yeah, I don't think there's much noise in the early part. This linear growth here is also true of entropy of a system out of equilibrium. The linear growth is related to something called Sinai-Kolmogorov entropy, Kolmogorov-Sinai entropy, which I suspect that my colleague Joel knows more about than I will ever know. But it's also a linear growth of entropy instead of complexity. Good. Now I want to come back to thermodynamics. And as I said, thermodynamics in the sense that 19th century steam engineers would have understood, they would have understood entropy as a useful resource for doing work. No, I take that back. They would not have thought of entropy as a useful resource. They would have thought of negative entropy, the opposite of entropy. Let's call it minus entropy. It's what Schrödinger called neg entropy, minus the entropy. That's the resource. You have a good resource for doing work when the entropy is not as big as possible. And so you could define something Schrödinger did define it. Well, he didn't define it in exactly the same way. Let's just call it neg S, neg entropy, which is the maximum entropy that a system can have. Now, there may be some constraints. The energy may be constrained or something, in which case the maximum entropy would just be the thermal equilibrium value. But let's not, I don't want to be too pedantic right now. Minus the actual entropy itself. It's the gap between the entropy of the system and the maximal entropy, and it's the room that you have for the entropy to grow, and therefore it's the room that you have to use the system to do work, or to work as a refrigerator, or what have you. And so that's what Schrödinger meant by neg entropy. And neg entropy is a resource. There's a whole formal theory of resource theory, which is very interesting. I'm not going to get into it. It's just a resource. If you have it, you can do something with it. All right, let me give you some examples of where you have some neg entropy. Imagine I have two boxes of gas. Let's suppose the gases are in equilibrium. And, very important, that they're uncorrelated. If they're uncorrelated, then, well, first statement is the maximum entropy, S max, of, let's call it 1 plus 2, of the sum of the two boxes. They're identical, thermodynamically identical in any case. The maximal possible entropy is just proportional to the total number of degrees of freedom, which is the sum of the maximal entropy in here and in here. So that would be, let's call it twice S max. And this thing without an index up here just means either one of the two boxes. Okay, that's all right. So the entropy, the maximal entropy of the whole system is this, and in particular, if they're both at maximal entropy, number one, and number two, uncorrelated with each other, not strongly correlated with each other, then the actual entropy of the combined system will be approximately, or will be, in fact, S max. Okay? What that means is you will have no neg entropy. These two boxes will not have any neg entropy. Two things are important. The first thing is that each box is separately in equilibrium if you were to look at it, and second of all, that they're pretty uncorrelated. Then, and what to conclude from that? You conclude from that you can't do work with it. No possible work. Now let me compare that with something else. Here are two boxes. Each one looks in thermal equilibrium, but they're in exactly the same microstate. This could be phase space rather than configuration space. It would make a little more sense. There's a molecule over here, which is exactly at the same position in phase space as this one. One over here, one here, one here, one here. Precise equality between the microstates. What is the entropy of this configuration? The entropy of this configuration is the same as the entropy of either box. Right. You don't double the entropy in this case. The very, very strong correlations remove a large fraction of the entropy. And basically, the entropy of this combined situation here is the same as the entropy of either box. Okay, so what do we learn? Let's calculate the neg entropy. That's equal to the maximal entropy, which is twice S max. Max here this stands for the maximal entropy of either of the boxes. The maximal entropy of either of the sum of the two boxes is twice that. But now let's subtract off the entropy of the actual entropy of the system. That's just minus S max. And that's equal to S max. In other words, there's a lot of neg entropy in this system here. And it's possible, in fact, this is one, you did show the perpetual motion machine that you made this out of, right? Was it out there?
Yeah, there is a perpetual motion machine outside.
Yeah, but it was based on this principle, wasn't it?
Well, the one outside is based on forgetting the entropy generated by someone.
Okay, well, I'm going to show you a perpetual motion machine, which is not really perpetual, but you look at either box and you see it in perfect thermal equilibrium, and you discover you can do work. Okay, so here it is. It's right here. You can come up and play with it and try it out and see if you can make it work. But that's it. Okay. So here's a curiosity. By putting them in exactly the same microstate like this, you can do a lot of work. All right, so what has this got to do with complexity? Complexity, as I've described it, is a kind of entropy. It was the entropy of an auxiliary system. Let me just quickly remind you. If your quantum system is described as a point moving on a Hilbert space, the evolution of a quantum system, as a point moving, let's say, on CPN, on the space of unit vectors in Hilbert space. Up till now, I've been using unitary operator complexity. I'm going to switch to state complexity. It's a subtle business, but let's just say the quantum system of interest can be represented, its state at any given time can be represented as a state in Cp 2 to the k minus 1. That's the dimensionality of the Hilbert space, 2 to the k minus 2 to the k. You subtract off 1 for reasons that are in the definition of a projective space. And now, at any given instant, if a system is in a state of some sort, it's localized somewhere, and then it moves through the system here. Okay. The number of coordinates describing this point is very high, 2 to the k coordinates. So it's analogous to having 2 to the k particles, the coordinates of 2 to the k particles. This thing is a gas, in a sense, of a large number of degrees of freedom. What are those degrees of freedom? You could take those degrees of freedom to be the expansion coefficients of the set of expansion coefficients, which are simply coordinates on the space here. And we could think of each expansion coordinate as being the coordinate of a fictitious particle. We have 2 to the k particles moving around, enough particles easily to do statistical mechanics. And another way we can write this is we can say this is a column vector, alpha 1, alpha 2, and these are the coordinates of the auxiliary system. The entropy of this auxiliary system is the quantum complexity of the original quantum system. Okay? All right. That's the thing which we've been talking about up till now. Now what I'd like to do is to build a system which has a richness of 2 copies of this auxiliary system. Well, you might think the thing to do is to take 2 copies of the quantum system. But 2 copies of the quantum system, how many parameters does it take to describe a state of 2 copies? Not the sum of the number of coordinates here plus the other one, but the product. So that's the wrong idea. The right idea for building a system which is 2 copies of the auxiliary system is to add 1 qubit. 1 qubit will double the dimensionality of the Hilbert space. And so the new Hilbert space with the extra qubit added, alpha to 2 to the k, and then we start over, beta 1, beta 2 to the k, where the betas are the components of the wave function which are correlated, let's say, to the extra qubit down, whereas these are the extra qubit up. This has twice as many coordinates, and it is as rich as a system with twice as many degrees of freedom. And it is the right way to think about doubling a system in terms of complexity. Okay, let's take an example. Let's define the following state. Extra qubit in state 0 times max 1. Now what does max 1 mean? It means a pure state whose complexity is maximal. And let's add to that plus 1 times max 2. Roughly speaking, this is 2 gases in which each component of the gas itself is maximally complex, and that means it's in complexity equilibrium. Okay? One more thing. I'm going to assume that the relative complexity of max 1 and max 2, that's the number of gates that it would take you to go from max 1 to max 2, is also maximal. That effectively means that the 2 gases are as uncorrelated as possible. Very, very uncorrelated. This is very much like the 2 boxes of gas, but now not the 2 boxes of gas, but now the gases, the coordinates of the gas are these labels, where each one is in equilibrium, uncorrelated with each other. What is the complexity of this state? The complexity of this state is maximal. Maximal means complexity 2 to the k plus 1. The extra 1 comes from the extra qubit that I added. So the complexity, let's call this psi. The complexity of psi is 2 to the k plus 1, which is the maximal possible complexity for a system of k plus 1 qubits. And therefore, this has maximal complexity. And a language I will use, I toyed with using the term neg complexity, the difference between complexity and maximal complexity. I didn't like neg complexity. I never liked neg entropy. You know who invented the term neg entropy? It was Schrödinger in his book on life, on what is life. He was interested in how being below maximum entropy can allow you to do interesting things. But in any case, Adam Brown and I started calling the following quantity, let's call it C max, maximal complexity, minus the actual complexity. We started calling this uncomplexity. What's that? What's that?
Simplicity. Simplicity.
No, I didn't want to call. No, you can have a lot of uncomplexity and still be pretty damn complex. So I didn't like that. So then I didn't like the asymmetry of the subject. So we tried calling neg entropy untropy, but you know, that's simply not going to fly. So there's neg entropy and uncomplexity. Okay, so the system that I built by taking 2 maximally complex states, combining them with a qubit in that manner, and making sure that the 2 maximally complex states were as relatively complex as possible, gave me something with 0 uncomplexity. Absolutely useless, but useless for doing what? We're not talking about entropy and lifting weights. The conjecture was that it had to do with computational work. What does computational work mean? For the moment, just it means ability to do computations with a system. And I'll give you an example, a very clear example. But this system is so maximally complex that you can't do anything with it. In the same way that you can't do anything with a maximally entropic system. Okay, let's take another state. This other state is similar, but it would be called having a clean qubit, and I'll tell you what that means in a minute. It means the same kind of thing, 0 max, 1 plus 1 max 2, except that max 1 and max 2 are the same, exactly the same. So what is this? This is just a qubit in the state 0 plus 1 tensor producted with the maximally complex state of a bunch of other qubits. The complexity of this is about the same as the complexity of max here. You have 1 extra qubit in a linear superposition of states. The complexity associated with having made 0 plus 1 is negligible. It's at most 1 bit of one unit of complexity. And the maximally complex state here is the same as the maximally complex state here. The complexity of this is essentially just C max. Okay? On the other hand, the maximal complexity of the whole system is 2k as e to the 2, sorry, Ahmed? Oh, no. Right, okay, this is the actual complexity of the state. The maximal complexity of k plus 1 qubits is 2 to the k plus 1. This C max, the actual complexity is minus 2 to the k. It's very much like this box of gas, or the 2 boxes of gas in the same microstate. So the uncomplexity this time is 2 to the k. You've somehow bought yourself, by adding 1 qubit, you've bought yourself this very, very large uncomplexity. If uncomplexity is somehow a resource for doing something interesting, what you've done is by adding 1 qubit to an exhausted computer which has run itself down into the ground and become maximally complex, you have rejuvenated it. Bought yourself an additional 2 to the k units of uncomplexity. And that sounds interesting. Of course, it sounds a little bit crazy that by adding 1 qubit, it sounds like almost like saying you've added 1 molecule to a gas. The molecule's out of equilibrium, okay? How much weight can you lift if you add 1 molecule to a gas of 10 to the 30th molecules? Not very much. Okay, so it sounds unreasonable that by adding 1 qubit to a quantum computer that has run itself to complexity equilibrium, that you can do anything interesting with it. So I went to, when I started thinking about this, I went to Patrick Hayden, and I said, Patrick, I have a crazy conjecture. I have the crazy conjecture that if we add 1 qubit to a maximally entangled, or I keep saying entangled, to a maximally complex state, we can suddenly do lots of computation with it. And he said, sounds like something I once heard about called 1 clean qubit computation. So he sent me to some references for 1 clean qubit computation. The reference that ultimately helped me understand it was the original reference to it, which is by Laflamme. Laflamme is the same Laflamme who discovered the Gregory Laflamme instability in black holes, and Knill. These are 2 computer scientists now, quantum computer scientists. So he sent me to this reference, and here's what I found out. Yes, indeed, adding 1 clean qubit can allow you to do very complicated computations. Now, it's not clear how universal it is. In fact, it's quite clear that it's not very universal. But there's at least one very complex kind of calculation that it allows you to do. It's calculating the trace of a matrix, a trace of a unitary operator in the space SU2 to the k. Just calculating. In other words, supposing I give you a unitary operator. Let's call it G. Two to the k qubits. G is an operator in that space, unitary operator. And let's even suppose that we could decompose this into a product of gates. G1, G2, and so forth. So in fact, perhaps we even know what the complexity of G is. The complexity of G is the minimum number of gates that it can be decomposed into, but let's suppose that, it's presented to us in this form here. And it's just some, in fact, we might not even know what G is. It's just given to us in a box, and we can insert it into a circuit. Or we might even know what it is. Why is it so hard to compute the trace? And the answer is extremely simple. It requires adding up 2 to the k numbers. That takes a lot of computer power to add up. So as a classical problem, this is a very complex problem. Okay? Let me show you how to solve it using one clean qubit. Here's the circuit. The circuit starts with this state maximally complex, okay? And there's one extra qubit. It's our extra clean qubit that we've added in the state in which max 1 and max 2 are the same. All right, so it's extra, a clean qubit not entangled with the rest of the system. And now here's the circuit. The circuit is very easy. We begin with a Hadamard operation. A Hadamard operation just takes sigma up to up plus down, sigma down to up minus down. So it's just a simple rotation in space that rotates the z-axis to the x-axis. Hadamard, we're going to start this qubit in the state O. Down, okay? Hadamard converts it to the state up plus down. And then we do a controlled operation over here. A controlled operation means we do the operation if this spin is up. We don't do the operation if the spin is down. And then we do a Hadamard again. Okay. At the end of this, we do a measurement. We measure sigma z. This is the whole circuit. Now you might say, this is a very complicated circuit. It doesn't look k-local to me. It doesn't look like the kind of thing that we can do easily. Here we have a whole big operation here, but in fact, we can show that this is quite possible to do. We can break it up into a k-local circuit. Let me just draw it. The which? The pink circle.
The dot.
This one over here.
Yeah.
Oh, that's the symbol for a controlled operation. Who asked me?
Which operation?
Mm-hmm.
It's a controlled operation, but is it not controlled not?
No, it's not controlled. It's controlled G.
Okay.
Right. All right, let me just explain what a controlled operation is. This is you think of this as a control qubit. Right? What does it control? It controls whether or not you do the operation G. A C-NOT gate is one in which you do a NOT operation. What is a NOT operation? It takes up to down and down to up. A C-NOT operation is a controlled operation where if the spin is up, you flip the other one. If the spin is down, you do nothing. That's the idea of a controlled operation. Okay. So here, so let's suppose G here was decomposable into some k-local gates. I better spread them out because otherwise I won't have room. Is not what?
Is G a complicated operation?
Could be.
Okay.
I don't think I want it to be maximally complex. But even if it's not maximally complex, this is very complicated simply because you have to add up 2 to the k numbers, and nobody ever found a simple way to do that in general. So to do it other than to add up the 2 to the k numbers. Okay, so here's your control qubit, and I'll draw the same circuit here in the following way. First, I do my Hadamard. Then I do a controlled simple gate over here. And then, just to jazz it up, I'll put another Hadamard here and another Hadamard. They cancel each other. And then a controlled gate over here. Hadamard, Hadamard. Controlled gate over here, another Hadamard. The reason I'm putting on all these Hadamards is to construct a structure here. Hadamard, control, Hadamard. And notice that this whole structure here is quite k-local. If these things are too local, then at worst we encounter 3 local gates here. It's a product of 3 local gates. And that is the same as this. You can check, I mean, just sit down for a minute and you'll convince yourself that this is the same as this. So we're doing a kind of sequence of operations. And now, this is an exercise. I'm not going to do the exercise on the blackboard, but it's a really easy exercise. Take this sequence of operations here, apply it, and ask what you get in the end. Once you get what's in the end, ask what the expectation value of the z component of this extra qubit is. What's the expectation value? Let's call it sigma z, after you've done the operation. And I'll write it out here. This is the world's simplest protocol. It takes 2 minutes to do it, but sigma z will equal 1/2 the expectation value in max of G plus G dagger max. Okay. That's what you get. Good. Now, where am I going to use the fact that the state is maximally complex? Well, if a state is maximally complex, you can replace it by a Haar random state. And you can evaluate this by averaging over the SUN group. You can evaluate it by just doing a Haar randomization. And what you get from this, for a maximally complex state, for almost all operators, is that it's equal to 1/2. The expectation value is now just given by the trace of G plus G dagger. And as usual, what I mean by the trace is the normalized trace, so that the trace of the unit matrix is 1, so that the trace of 1 is 1. In other words, you divide by 2 to the k in here. Okay, what we've succeeded in doing is producing a state in which the expectation value of sigma z is exactly the kind of trace that we're trying to compute. Incidentally, if you, instead of measuring sigma z over here, you measure sigma y, then you'll get G minus G dagger. So you can get either G plus G dagger or G minus G dagger. Now, this doesn't give you the trace. It gives you a state in which the expectation value of this spin over here is equal to the trace. You have to do this multiple times, let's say 10 times or some number of times, and collect some statistics in order to find out some information about the actual trace. That's not considered part of the computation. That's stuff you do afterwards. The computation itself, think of as just the labor involved in getting to this state, getting to the state that has some good information in it. Then you measure it and do stuff with it. And that's the story. Okay, so we've exhibited the ability to use a maximally complex state, which we could not do anything with, add one clean qubit to it, and we suddenly find ourselves capable of doing very complicated, there are problems in computer science which involve calculating the trace of something. Calculating Jones polynomials is one of them. Okay, so one clean qubit computation can do difficult things. Yeah. What's that?
So uncomplexity, so it makes, I think it makes sense to define Neg Entropy as a resource.
What's that?
Entropy is extensive, but complexity is not, right? So why don't
Complexity is not extensive if you combine quantum systems. It's extensive in this sense here. You add one qubit, and that doubles the maximal possible complexity.
but then why don't you define the resource as,
What am I going to do what?
why don't you define the resource as Cmax divided by 6 instead of minus 6?
Can somebody, I can't hear well enough to.
Why don't you define the resource as Cmax divided by C instead of Cmax minus C?
I was just following my nose, mimicking thermodynamics, mimicking the thermodynamics of, and thinking in the back of my head that complexity is a form of entropy, and I'm asking for the parallels between ordinary thermodynamics, which is entropy-oriented, and the thermodynamics of complexity, which is complexity-oriented. So I just intended to build everything in parallel and see where it went. But what I realized was that doubling the system, doubling the auxiliary system, which is basically just the wave function, does not mean doubling the quantum system. It means adding one qubit. Okay, so it really is true that adding one qubit gives you immense power that seems crazy. Yeah.
So here, so we can use this method to measure the sigma of Z to calculate the trace of some gate G, right?
Yeah.
But if G is some simple gate, then would that be easy to evaluate the trace directly? Because
Well, if G was one gate, and you knew that it was one gate, sure, you could, it's a 2x2 or a 4x4 matrix. It's easy to calculate it, right? But supposing somebody gave you G and didn't tell you what it was. They just gave you a box, and you plug in on one side and you plug in on the other side. You don't even know what G is. This will give you its trace. So, good. Well, this calculations will give you its trace. Okay, have we expended uncomplexity? Because when you do work, you expend, or it's really free energy, but remember, free energy comes in with a minus S, but you use up your neg entropy by doing work. You expend it. Question, how much uncomplexity have we expended? Okay, suppose we started the system far from maximal complexity. This one had maximal complexity. By adding an extra qubit, we converted it to a system which was still very far from maximal complexity, and then we started applying some gates. The natural expectation is that unless there are collisions in the sense that I defined them in the first lecture, the natural expectation is that we have increased the complexity by the number of k-local gates that we've applied. How many is that? That's the complexity of G. So it looks like we've increased the complexity of the whole system by the complexity of G, and that means we've decreased the uncomplexity also by the complexity of G. By measuring or by computing the trace in the sequence of steps here, at each step, roughly, we decrease the complexity by one, we decrease the uncomplexity for each step by 1 unit, and in other words, to carry out this process, we have to expend a uncomplexity equal to the complexity of the operator whose trace we're calculating. It's like doing work. We have the sequence of things. Each one of them can be thought of as pulling a pulley up a little bit, pulling a weight up a little bit. The sequence of them pulls up the weight a lot. How much entropy do we have? How much neg entropy do we have to expend? The number of little poles. Very similar thing. Yes, one.
Yeah, I'm confused on whether we should include the measurement or not.
No, the rule. Okay.
If we include the measurement,
Yeah. The rule that computer scientists sometimes use is to say the resource that you have to expend is the resource that you have to expend to produce the state which has the information in it. For this purpose, you don't count the, it's just the question of how much computation do you have to do to get to a state. And then you have to do it a lot of times, it's true. So in terms of resources, you also have to provide the resource of being able to do this many times.
I'm confused by the fact that by just measuring 1 qubit, we suddenly gain a lot of uncomplexity.
By adding, wait, we,
Measuring 1 qubit. So let's say you have the very complex state.
Yes.
You measure 1 of its qubits.
yes. Oh, I see.
Like a 1 qubit.
Yes, this is true.
I mean, you transfer
This is true.
to the measurement
This is true.
and so on, but
This is true. Of course, if you measure all the qubits,
well, then,
right, okay, so I think the buzzword here is interested in reversible processes. Let's talk about the class of reversible processes. So measurement is not allowed. It's true, you can get rid of all the complexity by making a measurement on all of the qubits, for example. That gets, it puts you in a totally unentangled state, but you have to, that's not very reversible, and it will heat the system. Let's suppose we have to do our operations without heating the system. That would be the idea here. But for whatever it's worth, this is the kind of thing that you can do with the extra qubit that you couldn't do with a maximally complex state without the extra qubit. So as I said, this is called one clean qubit computation. Let's see, I have a moment or two to tell you about the relationship between uncomplexity and black holes. Yeah.
So if I think of the microcanonical ensemble,
If I,
the microcanonical ensemble, and I think of that entropy is counting the number of states consistent with some macroscopic variable. What's the macroscopic variable equivalent in the complexity story?
I'm not understanding.
All these alphas consistent.
Yeah. I guess I don't understand the question, Edward. Let's talk later. I got about 5 minutes and okay, so. As I said, it's a struggle enough for me to hear what people are saying, let alone to, okay. What is uncomplexity in black hole physics? There's a very simple picture that I'll draw for you. Let's take the one-sided black hole for this purpose. Here's the one-sided black hole. Time goes up. Let's say the black hole has been formed sometime in the past from some simple, unentangled things, and it has low complexity to start with. Its complexity increases, and then it reaches some maximum. Let's put a little cutoff, a little slash up here to indicate where the complexity becomes maximum. According to my assumption, if the complexity becomes maximum up here, firewalls may eat you, and so the interior of the black hole is no longer available after an exponential time, according to this assumption, according to this unproved, unsubstantiated claim that generic states have firewalls and therefore block off the interior of the black hole. Okay, here's our horizon. Oops. There's our horizon. And now I'm going to use something I didn't talk about, I think. I don't remember talking about the complexity equals action conjecture, but I'm going to assume you know a little about it. If not, well, do the best you can. Okay, here's Bob over here, and Bob wants to know if he should jump into the black hole. He wants to know how complex it is and how much available space-time behind the black hole he can expect to be able to visit. That's his resource. His resource is available space behind the horizon. Okay, let's calculate the uncomplexity associated with Bob's state at time, let's call it T-Bob. Well, first of all, there's maximal complexity. The maximal complexity is the action associated with this whole region here if you went up to the maximum time at which it becomes maximally complex. Up here, the system has become maximally complex. The Wheeler-DeWitt patch associated with this point over here, its action will be Cmax. So let's simplify it a little bit. The volume of space-time, the action represented by this region here is Cmax. Let's just call this equals Cmax. And it just means something proportional to the volume of this region up to this exponential time. Now, what about the actual complexity at Bob's time? Well, his Wheeler-DeWitt patch looks like this. The region behind the horizon, which governs his complexity, or the complexity of his quantum state, is this region over here. So the blue region here is just C, or the complexity at Bob's time. Let's call it complexity at Bob's time. What's the uncomplexity? It's the difference between these two, and therefore is the action or the volume of space-time in here. Between here and the time that everything maxes out, and Bob must not fall in at that time because he gets burned up. What can we say about this region? This region is the entire region that Bob can visit. Now, if he jumps in, he may not be able to visit all of it, but if he jumps in at different times, this is the available possible space-time that Bob can ever visit. If we think of that as a resource, then we would say that the uncomplexity in black hole physics is just available space-time that somebody outside the black hole can expect to be able to visit. So it has a geometric meaning, or geometric meaning in general relativity. And good. One last thing. When you've used up, let's draw another picture here. When you've used up all the complexity, in other words, when you're up here, when Bob is up here, and he's used up all the complexity, all the uncomplexity, what can he do to make sure that when he jumps in, he won't get killed? The answer is drop in one more thermal photon. Adding one thermal photon takes the complexity from what was originally Cmax and multiplies it by 2, or in other words, the available uncomplexity becomes equal to the uncomplexity at the starting point before anything else. He's renewed and restored the black hole, or at least the black hole interior. This is just this point that I drew before, that if we have this picture for the growth of complexity, and then somebody throws in one more qubit, they double the maximum complexity, and in that way release a whole new time, as long as the original time, during which complexity can increase, and therefore, according to the hypothesis, the black hole will no longer have a firewall for another exponential time. Okay, that's the end of my lectures.